This is a continuation of our previous lecture, that is on ceramic gas sensors. We did discuss about the response or the sensitivity of the gas sensors, the semiconducting gas sensors, and that was the typical curve where different gas have been introduced at different times and the response or the sensitivity increases as the gas concentration increases. In this case, C1 is less than C2 and still less than C3. So, C3 is the highest. So, as we increase the gas concentration, the total change in resistance increases, and as I just discussed that it may or may not be completely linear, but within a certain range certainly it is linear and one can use it for some control systems. Right. So, this was the response time. As I mentioned also, the response time and the sensitivity can be changed to some extent or modulated to some extent by different parameters. One of course important parameter is the temperature, and temperature changes the adsorption characteristics of different gases. So, you can make a relative changes in the response characteristics to specific gases. That is one way of doing that. And overall, once the temperature changes, of course, there is a difference, there is two different opposing factors. Temperature changes of course increases the kinetics of the process, but also it can lead to desorption of gases, desorption of oxygen in particular, and that may lead to reduction in the sensitivity or lowering of the sensitivity. So, one has to optimize which is the best temperature at which the system has to be operated. There is another way to enhance the sensitivity. This is through so called nanotechnology. Of course, this is nanotechnology in the sense here basically use nano powders instead of micro size powders to enhance the surface area, so specific surface area. Because we have seen the property is basically controlled by the surface property. So, its adsorption, desorption is the surface property, and that leads to the surface conductivity and so on. So, if you can enhance the surface area, specific surface area of the material, particularly powder in this case, one can certainly enhance the selectivity sensitivity of the sensor. So, introduction of a nanotechnology is a very convenient way to enhance the sensitivity of the process, and most of the powders incidentally are made by different kind of chemical synthetic processes. Okay. Either may be a sol-gel process, it may be co-precipitation process, it may be prepared by hydrothermal processes and so on. So, these chemical processes always lead to very fine powders, sometimes micron size powders, sometimes nano size powders. So, we have some control, on the surface area of these powders, which are ultimately will be used for the construction or the design of the sensor. So, by making nano powders, one can enhance the surface area, and therefore, the sensitivity can also be improved. So, there is an example of that here, just a schematic again. Once again we have plotted the time or the sensitivity against time, and two types of powders, two types of same powder, same material, either tin dioxide or zinc oxide, sometimes maybe different other oxides, nickel oxide or cobalt oxide and all that. But as I said earlier, these are the two oxide mostly used, and this is micro size powders, micron size powders, and this is nano size powders, and you can see a fair amount of enhancement, all other parameters remaining same, just by changing the particle size of this ceramic powders used for the fabrication of sensor, one can enhance improve the sensitivity property. So, that is an important criteria or important aspect must be remembered in designing the sensors. I think that is all. Before I go to another topic, I should mention that semiconducting gas semiconducting oxide based gas sensors are still under development, and many sensors have been already commercialized or marketed, but still further developments are being taking place, and many of the research work is still also going on in this country in different groups. Some of them, for example, are very active to develop like the ceramic nose. The others are discrete sensors for things like breath sensor. Okay. Somebody consumes alcohol, it can be detected from the breath how much percentage or how much if there is residual alcohol there. So, alcohol sensors are also available. Very recently something different is being tried. Acetone can be sensed, and it is understood that if somebody is a diabetic patient, the acetone concentration in the blood increases, and from that one can really measure the diabetic state of diabetics in somebody's health. And so, there is a these kind of sensor are basically gas sensors for industrial purposes, but also can be applied for some medical treatment, medical diagnostics. So, many applications, new applications are being thought of, and possibly in near future some success will come up in those areas. With this we change over from semiconducting oxide based sensors to a different kind of sensors, which is called zirconia based oxygen sensor. This is basically needed for oxygen gas sensing, not for any other gas, but there are tremendous importance of sensing the oxygen concentration under different situations. And in such situation, particularly when it is used or is needed in slightly elevated temperature, then this is one of the best sensor one can think of. It is more reliable, and it has a wide range of applications. So, let us try to discuss what is the basic principle on which a zirconia based oxygen sensor works. Zirconia basically a high temperature oxide, but one of the important criteria of or important property of zirconia is as a very high oxygen ion conductivity, particularly when it is stabilized with calcium oxide or yttrium oxide like that. It stabilizes, in fact, addition of zirconium oxide, addition of calcium oxide to zirconia not only stabilizes the cubic fluoride phase, which is normally a high temperature phase at room temperature, but also enhances the oxygen vacancy concentration in the structure, okay, by a process like this. Because zirconia is a divalent, whether zirconia is tetravalent, whereas calcium is divalent. So, there is a deficit of two positive charges. So, when that is what is been written in this defect equation, calcium goes to the zirconium side, and there is a effective two negative charges created, and to compensate that you have to have effective positive charge, and that is by oxygen vacancy. Okay. So, you create oxygen vacancy by adding calcium oxide to zirconium dioxide, you actually enhance the oxygen ion vacancy concentration, and that leads to a very enhanced mobility of oxygen ions and high oxygen ion conductivity. This is a very typical material where in the solid state you have very high oxygen ion conductivity, no electronic conductivity, almost nil electronic conductivity. So, the Ti, what is called known as the transference number, for the oxygen ions is very close to 1, and this is Ti by T sigma I by sigma T, that is the total conductivity and the conductivity arising from the oxygen ion. So, this is very close to 1, this is very close to 1, more than 0.99, and that is one of the requirement for using this material as an electrolyte in some of the electrochemical systems. But before we come to that, these are the conductivity plots, okay, electrical conductivity of various oxygen ions and conductors, particularly which are those are known as solid electrolytes. So, they can be used as electrolyte in a solid state electrochemical cell. So, these are mostly cubic fluoride type oxides, and this starts with thorium. TiO2 also has a cubic fluoride structure, and Bi2O3 at a slightly elevated temperature, one of the polymorphs is also a cubic fluoride structure. So, CEO2 is another oxide which has a cubic fluoride structure, and all of them whether it is zirconia, thoria, ceria or Bi2O3 bismuth oxide. So, these are all characterized by high oxygen ion conductivity. Out of the, of course, their absolute level of conductivities are different, as you can see from here. While bismuth oxide has a very high conductivity at a fairly low temperature, but it is not so stable and it is little reactive, chemically reactive. So, bismuth oxide is normally not used, although it has a high conductivity. Zirconium oxide 7.5 mole percent, scandium oxide. Scandium, when you dope Sc2O3 scandium oxide to zirconium dioxide, it produces a very high conductivity. Unfortunately, this is again rarely used because of the very high cost of scandium, which is a rare earth oxide, and non availability of this particular oxide. Cerium oxide with 5 mole percent yttrium oxide, or cerium oxide 10 mole percent yttrium oxide, you have fairly high conductivities, and and they can be also used, they can also be used as an electrolyte. Of course, has some disadvantages, maybe I will discuss in a minute what are those. But the most important solid electrolyte is zirconia stabilized or doped with yttrium oxide, or zirconia 15 mole percent calcium oxide. So, yttria is normally preferred because it has a higher conductivity than that of calcium stabilized zirconia. Thoria on the other hand has a much lower conductivity. So, they can be used at very high temperatures, but normally it is costly, as well as there is some problem of radioactivity, and so until and unless it is absolutely essential, one does not use thorium oxide electrolytes. So, these are the relative conductivity, ionic conductivity of all our oxygen ion conductors, of course, of different electrolytes known to us. Well, this we have discussed when we are discussing about the defect structure of different oxides, and this is a generalized picture of partial pressure dependence of different kind of possible defects present in a oxide. Okay. So, in general, one can notice here that there are 3 partial pressure ranges. Okay. Broadly, they can be divided into 3 ranges. In the middle range, you will see either it is a n equal to p neutrality condition, or we can follow this, particularly for the oxide ion conductors. This is a more suitable diagram, where in the intermediate partial pressure range one can see the neutrality condition is VO, that means oxygen vacancy and oxygen interstitial. So, they becomes equal. So, it becomes a kind of stoichiometric oxide with anti-Frankel defect. This is an anti-Frankel defect kind of situation, and at a very high PO2, of course, what is high is not mentioned here specially, that will depend on the particular oxide which is high, but the characteristics changes. The high is basically characterized here because the nature of neutrality condition changes, and one changes from a constant value of these defects to an increasing value of the defect. That means, this one oxygen interstitial increases beyond this point. Beyond at lower oxygen partial pressures, this is remains constant independent of PO2, whereas beyond this point there is an enhancement in oxygen ion interstitial as a function of PO2. So, that is how this boundary is characterized, where it changes from PO2 independent region to PO2 dependent region. On the left is also similar boundary condition is there. Once again, from a PO2 independent region it changes to a PO2 dependent region, but in this case it is oxygen vacancy. Okay. The oxygen vacancy is the predominant defect on the left side, that is lower PO2, whereas on the right side oxygen interstitial is the predominating defect. Okay. Others have a lower concentration. So, this is dominated in this region, this is dominated by oxygen interstitial, whereas in this it is oxygen vacancy, and in between both of them are same, concentration wise they are same, and therefore, you have a independent PO2 independent conductivity. In fact, for our purposes this is the region, most important region, where it is not only independent of PO2, the conductivity, in fact, the vacancy concentration and the interstitial concentration are independent of PO2, and they give rise to conductivity. So, the mobile species, the concentration of this actually determines what will be the conductivity. So, the conductivity is proportional to this defect concentration, either oxygen ion concentration, oxygen ion vacancy concentration, or oxygen ion interstitial concentration. So, our interest is here. In this we have PO2 independent oxygen ion conductivity. On this region is PO2 dependent hole conductivity. Okay. Although interstitial is increasing in this, but the interstitial is also associated with hole conductivity, and therefore, this becomes an electronic conductivity in this case, and this is also purely n type conductivity on this case. So, this is our interest, where it is independent and ionic conductivity. In fact, if you plot the two most important oxides which is of our interest, one we have seen zirconia calcia. So, the 15 mole percent calcia doped zirconia, this is the variation of conductivity. These are experimental plots. So, one can see the conductivity remains independent of PO2 from almost atmospheric condition, that is pure air, to down to a very low PO2 like 10 to the minus 2 minus 22 atmosphere. So, it is a very reducing condition. Even at a extremely reducing condition, the zirconia remains as an ionic conductor, and it is dominated, the conductivity is dominated by ionic conductivity. Same thing happens here in thorium oxide, although the absolute conductivity is low. Here this has a higher conductivity, this is a lower conductivity, but you do not see a upturn here, because the material do not become electronically conducting or n type conductor even at 10 to the power minus 22 of atmosphere, whereas on this side there is a slight upturn at very close to the atmospheric oxygen partial pressure, you have a p type conductivity. Okay. So, this actually leads to an n type conductivity beyond certain partial pressure low in the low range or below 10 to the minus 22 atmosphere, whereas here above 10 to the power 2 atmosphere minus 2 atmosphere sorry 10 to the minus 2 atmosphere, this becomes slightly whole conductor or a p type conductor, but otherwise from 10 to the minus 6 or 10 to the minus 4 to 10 to the minus 22, both of them behave as an ionic conductor. So, that is important points to be noted. Okay. So, okay, go back to that. So, because this is the variation or the nature of variation of conductivity as a function of partial pressure, we can assume that within this range it acts as a good oxygen ion conductor, and so it can be used as an electrolyte in an electrochemical cell or sometimes called concentration cell. So, this is what one can represent an electrochemical cell. So, there is an electrolyte which is basically zirconia, zirconia calcia or zirconia yttria, yttria stabilized zirconium oxide, and then on either side you have a sample gas and a reference gas having two different partial pressures or oxygen potentials. So, reference gas, whatever the oxygen partial pressure of reference gas, we say it is mu 0 O2 or chemical potential, and that is related to the partial pressure PO2 0. On this side is mu O2 and PO2 0 PO2. So, this is one can say unknown PO2 oxygen concentration or oxygen partial pressure. This is a known one, that is why it is called reference. Now, if we make a oxygen concentration or electrochemical cell like this, and we can find out what is the from the Nernst equation, what is the EMF generated. So, there will be an EMF generated because in electrochemical cell it is an electrolyte and these are the two electrodes, one is anode and this is cathode. So, by that one can find an EMF generated out of this. So, this is minus mu O2 minus mu O2 0 by 4F. 4 is the number of electrons transferred during the reaction, oxidation reduction reaction, and that can be mu is nothing but RT ln PO2. So, you have RT by 4F ln PO2 by PO2 0, okay, or PO2 naught. So, this is the EMF. So, you by generating a electrochemical cell or constructing an electrochemical cell, that will generate an EMF. So, that can be measured quite easily, what is the electromotive force or EMF generated out of this cell, and that in this, if we know all others being known, the temperature of the cell has to be known and these are constants. So, if one knows this value, then this can be determined. So, that is the basic principle by measuring the EMF and correlating it to the partial pressure of oxygen by this formula. All others being known, one can find out what is the PO2 on this side. This is reference and this is the sample variable. Well, how exactly one can utilize it? For example, if you want to find out the oxygen concentration or the oxygen potential, oxygen partial pressure of a gas, you just simply take a tube, a ceramic tube, made of zirconia, stabilized zirconia. So, these are the this is one wall and this is the cross section basically schematics of this. So, this is another wall, same wall, continuation of the other side. You make a cell by just putting some platinum electrodes here. This is only for the current collection. Because gas is basically a gas electrode, so one cannot use the gas electrode for measurement or the EMF. So, use a current collector here or a contact. So, this is the black area is basically a platinum electrode and it has to be a porous platinum electrode because the gas has to come in contact with the electrolyte. So, this becomes the electrode. So, the gas has to come in contact or go to the travel to the interface between the electrode and the electrolyte. So, it has to be porous. So, one cannot use a platinum foil, but one has to use a porous platinum paint, that means a thick film of platinum. Okay. The reference gas, the outside is reference gas means air. Air has a very fixed, very fairly fixed oxygen partial pressure is nothing but 0.21 from the ratio of the nitrogen to oxygen. So, this is a very stable PO2, and if you have a gas mixture of oxygen with some inert gas, then that can be varied and or any other experimental gas. So, that a EMF will be generated between these two electrodes, the inside electrode, inner electrode and the outer electrode. Inner electrode is inside the tube and outer electrode is outside the tube. So, they are exposed to two different gases and that will generate a EMF. So, you measure the EMF and knowing the EMF of the the partial pressure of air, you know what is the partial pressure inside. So, this is a very simple setup to measure the oxygen concentration in a flowing gas utilizing zirconia oxygen sensor. So, the tube actually, the tube wall acts as a sensor, very simple thing. So, it is the functional property of the tube which is being exploited to make it a oxygen sensor, particularly oxygen sensor. Now, there can be another configuration, the same thing, only thing is instead of the wall being used as the electrolyte, here one end wall, because it is this was a both end open tube. So, the gas is coming from one side and flowing to the other side. Here we have a one end closed tube. So, the closed end can be used as also can be used as an electrolyte, and sense the partial pressure can be sensed. The only difference is the gas comes in and then goes to the strikes the flat bottom or the closed end, and then the other side or goes out from the same direction, whether the outside you have either air or different gas. Now, which side will be the reference and which side will be experimental, it depends on the requirement. In this case, the air is inside and the experimental gas is outside. So, depending on the requirement and depending on the situation under which it has to be used, both possibilities exist. That is, the inside can be used as an experimental gas or outside can be used as an experimental gas. There will be a furnace in both the cases, because the temperature is also important here, and to reduce the impedance normally these sensors are used above about 600 degrees centigrade, so that the impedance of the cell or the resistance of the electrolyte becomes sufficiently low for accurate measurement of the EMF. So, these are the two configurations in which zirconia oxygen sensors can be used to measure the oxygen partial pressure or the oxygen concentration in some of the experimental gases. Now, this is an industrially used oxygen sensor, same thing, basic principle remaining same, the design is slightly different. This is also a one end closed tube, it is not a flat end, but is kind of circular end. So, this whitish region is actually the electrolyte or zirconia. So, it has been fabricated in the form of a thimble, a small length one end closed tube, but not of uniform cross section or the wall thickness, slightly varying wall thickness. This is of course for mechanical advantage, and you have a slightly thicker wall towards the cold end, whereas in the hot end it is a slightly thinner. And then this is a kind of porous shroud which protects this particular thimble, and this black area is actually electrodes. Okay. So, this is the outer electrode comes to up to this end, and the lower electrode also comes through the inside wall up to this end. So, you can measure the EMF from these 2 points. So, this actually not only the whole of it is acts as the electrode, but the active electrode area, active cell area is basically this much, and these are the kind of lead. It can the painted portion basically acts as a lead and connection for the electrodes. So, this is a very simple system, but it has a tremendous of use. Let me see what is there. Yeah, this is actually the cross section of what you call the lambda sensor for automobile exhaust. Okay. The basic purpose of measuring oxygen concentration in automobile exhaust is to control the pollution. Okay. It is the oxygen potential which becomes a measure of what is the extent of combustion which is taking place inside the engine, and what kind of air fuel ratio one has to be controlled, so that a complete combustion takes place. Because if there is an incomplete combustion, then lot of carbon monoxide will be generated, which is environmentally hazardous, and therefore, all automobiles these days actually uses this particular sensor to control the combustion process and also enhance not only the fuel utility or fuel consumption, reduce the fuel consumption, but at the same time control the environmental pollution, so that no carbon monoxide comes out of the exhaust gas. So, this kind of a sensor actually is used at the end of the exhaust pipe, or at the beginning of not the end, at the beginning of the exhaust pipe. As soon as the gas comes out of the engine, in the exhaust pipe, this kind of a sensor, just like a spark plug, one can plug in this kind of a sensor and measure the output. Okay. This is a typical response. This is a typical response of what we call a lambda sensor, that is basically the ratio is called the lambda, and therefore, it called the lambda sensor. How it works? It operates at obviously at plotted at different temperatures. You can see 500 degrees to 900 degrees. Now, this is the normalized air fuel ratio. Normalized in the sense actual air to fuel ratio is about 14.5, but this has been taken as a stoichiometric ratio has been taken as 1, and either it is a lean PO2, lean fuel or a excess fuel. Okay. So, this is on the other one side, you can see this is the PO2. This is the PO2 is increasing in this fashion on this side, and the EMF is plotted here. Okay. So, the EMF is very low in this region, whereas EMF is very high on this. Okay. It is basically the reference PO2 is again air. So, compared to air, if the PO2 is very low, then you have a very high EMF, whereas if the PO2 is very close to air, then very low PO2, very low EMF. So, this variation is just like this. It has a very high value on the reducing condition, whereas a very low value on the oxidizing condition. So, there is a discontinuity. There is a discontinuity exactly at the stoichiometric ratio. So, it is very sensitive in that case. That is the reason the sensors are highly sensitive around this value. So, if a very small change in air fuel ratio, the EMF drops, or if it is slightly above on this side or lower side, then you have a very high PO2. So, this is actually very important from the sensing point of view. So, one can electronically control or through the carburetor. Carburetor can be electronically controlled from taking the this input or taking the value from this. So, one can determine whether it is the high fuel ratio side or the low fuel ratio side, and therefore, the carburetor can be controlled and one can find out the stoichiometric combustion. So, that is very important from the point of view, as I said, from the environmental point of view as well as from the fuel economy point of view. So, that is the reason most of these, almost all the advanced car today have this kind of a lambda sensor, right, and that is based on Zirconia sensor. It is very stable and life is very long. So, there is no problem. Of course, one thing I forgot to mention, that along with the lambda sensor, one always uses a catalytic converter. So, that is a catalytic converter in which the exhaust gas is allowed to flow through that, and it has certain catalyst, normally some noble metal catalysts, and they catalyzes the carbon monoxide, remaining carbon monoxide into carbon dioxide. So, no carbon monoxide actually comes out, although you cannot avoid the release of carbon dioxide. So, the only thing is, so that is the whatever small amount of carbon monoxide, even after this control, small amount of carbon monoxide may come up, but that will get oxidized on the catalytic converter. However, if the carbon monoxide concentration is very high, then the catalyst life goes down, and therefore, one needs to control the carbon monoxide concentration in the exhaust gas, which goes into the catalytic converter. So, these two devices, one is the sensing devices and there is actually a catalytic converter. These two has to work in tandem, so that the combustion efficiency as well as the environmental problems are eliminated. Now, in addition to this kind of gaseous measurement or the gas phase measurements, where one needs to measure the oxygen ion concentration of different gas mixtures of different industrial gases even. In fact, another very important area where these sensors are extensively used is in furnaces. So, just like in automotive engine, you have a combustion process going on in the industrial furnaces, even ceramic furnace, ceramic kilns. Many of the ceramic kilns today are fitted with oxygen sensors, Zirconia sensors or oxygen measurement sensors. Again, the purpose is primarily to control the combustion, okay, so that you get the complete utility of your fuel. There is no excess oxygen or excess air into the system. So, in automatic control of ceramic kilns, you have these sensors becomes quite handy, and most of the modern furnaces do have are fitted with this kind of sensor, so that the combustion process, the fuel combustion process can be utilized the controlled quite efficiently. So, that is another area where besides automobile there is a huge application of Zirconia oxygen sensors in combustion control of the industrial furnaces. In addition coming back to this picture, in addition to the oxygen concentration or measurement of oxygen concentration in gaseous system, one can utilize Zirconia systems or Zirconia sensors for the liquid systems also. Many of the metals do have some dissolved oxygen, or sometimes there is oxides present in the metal. So, there is an oxygen potential, it may be large, it may be small, but oxygen concentration, measurement of oxygen concentration in molten metals or molten alloys is also of very great interest. Okay. And the same Zirconia system can be used for measurement of for creation of a electrochemical cell, and one can measure that. This is one example where this whole crucible, you can see the crucible is basically made of recrystallized alumina having some molten metal, and this is your molten metal, this is an alumina, this is in cermet, okay, and this is the tube, this is the one enclosed tube, okay, one enclosed Zirconia tube. This actually acts as an electrolyte which is dipped inside a molten metal, and this once again the wall is acting as the electrolyte. Inside you have a reference electrode, and outside you have in contact with the molten metal. So, by that process it generates an EMF. So, that is a measure of what is the oxygen potential of the molten metal, and the reference electrode here is of course of different types, not in AR as a reference electrode, but a different system has been used as a reference electrode. It is a mixture of nickel oxide and nickel and nickel oxide, okay, metallic nickel and a mixture of metallic nickel and a nickel oxide. Okay. Now, this also at a particular temperature it has a definite oxygen partial pressure, because just like it is an equilibrium partial pressure between metal and metal oxide. Okay. So, nickel when it oxidizes to nickel oxide at a particular temperature, it corresponds to a specific partial pressure of oxygen. So, whenever there is a coexistence of nickel and nickel oxide, then a specific thermodynamically a specific partial pressure is maintained. So, as long as nickel and nickel oxide are coexisting, that partial pressure will never change. Of course, it will change if the temperature changes, but otherwise that partial pressure, knowing the temperature, one can fix what is the exact partial pressure for nickel oxidation, and by that same technique one can use this mixed oxide as the reference electrode. So, inside you have a mixture of nickel and nickel oxide which maintains a reference electrode. Outside you have a molten metal which has a for which we want to measure the partial pressure of oxygen. So, it generates an EMF between reference electrode and the molten metal, and the electrical contact here is through a cermet. Okay. Here this is a cermet which is a conducting material, and it is immersed in molten metal. So, through the molten metal it actually connects this surface. Okay. So, the inside you have a reference and outside you have the metal, and the connectivity or the contact is made through this immersed cermet and molten metal being electrically conducting material. So, it contacts up to this point. So, actually it measures, if you measure a potential between this, there is a platinum electrode, platinum wire there which connects this surface, and therefore, between this platinum and this platinum here, the surmet is also connected to another platinum wire. So, between these two platinum wire you will get a EMF which represents the oxygen potential of the metal. So, the dissolved oxygen or some other oxygen potential in some other way, there will be a thermodynamic equilibrium and certain oxygen partial pressure are normally available. So, sometimes it is very important to measure those partial pressures for different purposes, and this is another setup by which one can use zirconia for measurement of oxygen sensor, measurement of oxygen concentration. This is thermocouple which just measure the temperature, because if you remember the Nernst equation, you also need to know the temperature. So, the precise measurement of the temperature is also important if you want to measure the oxygen partial pressure by this process. This kind of system is extensively used in steel melting. Okay. Steel melting is nothing but an oxidation process. From pig iron, you are oxidizing carbon, very high concentration of carbon, and then you are making steel with very low concentration of carbon. So, from 3 to 4% of carbon, you are bringing it down to about 0.2, 0.3%, maybe still lower. So, actually you have to oxidize the carbon, by that process you make steel. To monitor the oxidation process of the pig iron within the LD converter, you always need to monitor the oxygen concentration or oxygen potential available in steel. So, these are some of the designs designs of oxygen probes, they call it oxygen probes to measure the oxygen concentration in steel. These are of course a slightly different design, and you have a small molybdenum wire. Then this is actually a very small tablet of zirconia calcea fitted inside a quartz tube. Okay. So, it has been sealed, actually it has been sealed. The whole tube is not made of zirconia oxygen because it becomes costly. So, instead of that, certain sealing technology has been used, so that at the end of a pure silica tube one can have a tablet of zirconia, and that tablet zirconia acts as the electrolyte. It is one side it is connected to the steel, molten steel, the other side there is a electrolyte, there is a reference electrode, and in this case the reference electrode is not nickel oxide, it is actually chromium oxide. So, it depends on what kind of partial pressure of oxygen you are expecting in steel. Since the partial pressure of oxygen in steel and at a very high temperature is fairly low, you need a not nickel oxide, but a chromium oxide. Okay. So, a chromium oxide acts as a reference electrode inside the silica tube, and at the end of the silica tube zirconia calcea disc has been fitted, and that is exposed to steel, molten steel. Of course, there is a shroud to start with. This is a steel shroud, it is actually immersed in the liquid steel at a temperature of about 1600 degrees centigrade, and at that temperature this cover melts, melts, and molten steel comes in contact with this surface. Otherwise, it is protected by a steel cap. So, it is a steel cap which melts at the molten temperature, molten steel temperature, and exposes this electrolyte to the molten steel. And then there is another silica in the form of a silica U tube which contains the thermocouple. So, this measures the temperature, and there is a molybdenum rod which actually comes in contact with the liquid steel and makes the contact. on this surface. Okay. So, this becomes a contact. So, it goes up and finally, you measure the temperature measure the EMF between inside and the outside. Okay. That is how one can measure the temperature. It is actually a disposable type of sensor, because it cannot stand for too long at that very high aggressive temperatures. So, it is a kind of disposable sensor. Once it measures, it both measures the temperature and the EMF, and it gets melted away in the molten liquid. This is another design, but let me not discuss this particular design. Is very similar purposes used. So, those are the various applications, the principles. The principle of the operation of sorry. Principle of operation of Zirconia oxygen sensors in basically an electrochemical system, electrochemical cell which produces some EMF between the two different partial pressures, one partial pressure being known, other partial pressure can easily be determined. The last topic in this series is humidity sensor or moisture sensor. These are not well, we have used discussed two varieties of sensor. One utilizes the variation of conductivity as a function of gas concentration, that is the semiconducting oxides. Other we have seen the oxygen ion conductivity or electrolyte. So, we measure the EMF, and EMF it becomes proportional to the partial pressure of oxygen. Here we do not measure the conductivity or the EMF, we measure a capacitance. So, it is basically a insulating variety of oxide and a porous oxide, in general a porous oxide. So, within the pore, depending on the percentage of condensed moisture, the capacitance changes. Okay. Basically, the moisture has one kind of dielectric constant and ceramic material have a different kind of dielectric constant. So, the capacitance value changes as a function of moisture content which is getting deposited into the pores of the ceramics. So, that is the reason it is a capacitive type of sensor. We are not measuring either the EMF or the resistance. Porous alumina is one of the common ceramics used for the purpose. Another material of course is magnesium titanate. So, there are few, just like a porous alumina can be very well used as a sensor of humidity sensor, just the capacitance changes and one can have the variation of capacitance as a function of moisture content. The electrodes are normally used on the surface. It is not the bulk, again it is not the bulk capacitance what one measures, it is basically a interdigitized configuration as we have seen in case of a SAW device. So, it is on the surface, the electrodes are on the surface in an interdigitized form, and that measures the capacitance. But below that you have a porous structure, and that pores contain different quantities of moisture depending on the humidity condition outside. So, that changes the capacitance, and the variation of capacitance actually is directly proportional to the moisture content. Other configurations have also been used in such a way that the moisture can easily come in contact with the pore structure of the ceramics. So, it is basically once again a kind of porous configuration of the electrodes, because otherwise the moisture cannot come in contact with the pores below the electrodes, and therefore, it cannot function properly. So, the design is important here. One of the design is interdigitized, but then isolated pockets can also be used. I am not going to the details of those structures, but basically I am going to discuss the principle. Gold or platinum paste is normally used as a porous electrode, the capacitance, capacitive sensor and also other absorptions based sensors are known for their nonlinear relationship with RH is relative humidity. So, one of the difficulties once again is a kind of nonlinearity once when we get. The empirical relation may be expressed as Cs by C0 equal to epsilon W by epsilon D. So, W is the wet condition and ED refers to the dry condition. C0 is the geometric capacitance of the sample, depending on the overall geometric size and shape, you have a capacitance value, and N is a factor related to the morphology of the pore structure of the dielectric. So, depending on the morphology, fineness of the pore, the overall porosity and all that, this N is dependent on those parameters. In a porous dielectric, the air in the voids is replaced by condensed moisture as the relative humidity is increased. So, higher is the relative humidity, more and more condensation takes place inside the pores, and that changes the capacitance value of the ceramics. And in a empirical formula, this effect known as the capillary condensation occurs where radii is smaller than the Kelvin radii. So, everywhere condensation cannot take place. Okay. It is a large pore, the condensation may not take place, and therefore, there will be not much effect of on the capacitance. So, the pore size, particularly the pore structure, has to be controlled in such a way that there is a condensation takes place in the within the relative humidity range of our concern. Okay. So, our interest, whatever the relative humidity you want to measure, depending on that the pore structure has to be designed properly, because RK is the Kelvin radii is related to different parameters, to gamma mw cos theta rho RT ln Ps by Pw, where gamma is the surface tension and mw is the molar mass, theta is the contact angle of that particular spore, and then that depends on the material of the pore or the material in which the pores are there. Rho is the density, R is the universal gas constant, and T is the temperature. So, there is a relationship with the surface tension cos theta, theta is the contact angle of that surface, rho density and so on. So, depending on that you have a particular size of the pore in which the condensation will take place. If the if this one is too large or too small, then condensation will not take place and the material will not be used, cannot be used as a sensor. So, just if you have an insulating material and the pore structure can be controlled in such a manner that the condensation takes place, you have a variation in capacitance, and by measuring the variation in capacitance it can be related to the relative humidity of the environment. So, this is how one can also use ceramic materials for the sensing of moisture, one kind of gas in that sense. Okay. So, we have discussed various types of gas sensors based on ceramic materials, based on whether it is a reducing gas or a combustible gas. In fact, I forgot to mention that the LPG sensors have been used in practice quite extensively based on tin dioxide sensors. So, tin dioxide sensors has been used quite extensively to measure the combustible gases, including the cooking gas. So, gas leakages can be determined by this. So, I think we have come to the close of our discussion with this say that this is the kind of distribution of different kind of sensors. Solid electrolyte sensor, Zirconia sensor is the maximum, and then you have metal oxide sensors here, catalytic bead sensors, we have not this electrochemical sensors, these are not of course the solid electrolyte sensors, the liquid electrolyte sensor, paramagnetic sensors are also available, infrared sensors are also available with different gases and many others. But you can see the Zirconia sensor is the largest volume of sensors available in the industry. Okay. So, with this we come to the end of this discussion on ceramic gas sensors, and thank you for your attention.